All right, so we're going to go through another function that we're going to make a sketch of its graph. So, we call it, curve sketching, but it's really, graphing, the function. And we want to essentially show the key characteristics. These are not going to be your, everyday simple linear functions with straight lines and, you can find the vertex and y-intercepts and x-intercepts with formulas. No, these are going to be some, complex stuff. So we got to use calculus and all the stuff we've learned smaller math, lives up to now. So these functions are a test of, how much you've come to learn, and, up to now. So no pressure, but these, are kind of cool to see how, all connects. So, again, some general things to keep in mind are the key characteristics of, of a graph, like the x and y intercepts, the domain range. Let me just show the list again, just not to blabber it out. But here, when in the first part of this lesson, show that key characteristics when you're analyzing the graph. Look at the x, y intercepts. Look for any symmetry, the domain range. Look where it's continuous and discontinuous. Look for asymptotes where it's differentiable, relative extrema. The concavity, of course, and the point of inflection. This is where the calculus comes in, and horizontal asymptotes and infinite limits. That's generally the set of guidelines you want to do. Now the order again, it just varies. Sometimes I'll go and do like the algebra stuff first, intercepts and all that before the calculus. Sometimes I'll do the calculus first. There's not, the step-by-step way to go in order. It just depends on what you got. All right, so here, let's identify the domain. Pencil the fading away. Domain. The domain, or it's defined everywhere, because then you can plug in any number in here, which is great. We have no point. We note that we don't have to worry about any points of discontinuity. The domain are all real numbers, negative infinity to infinity. While we're at it, let's find the intercepts. Yeah, x-intercepts. X-intercepts. Y equals 0. So when is this equation equal to 0? All right, so going back to your calculus, or not calculus, your algebra, algebra lessons, you got to factor. We're going to factor let's factor out like an x to 4/3. Let's do that. It looks like it's going to work. So we get 0 equals x 4/3 times 2x to the 1/3. I want to be able to squeeze it all in here. Minus 5. Minus 5. Let's see where this goes. Let's keep it over here. Actually, let's carry it over here. So then, okay, so we have a 0 here, x equals 0, and then we have so you have 1 0 at x equals 0, that one x-intercept at x equals 0, so at 0 0, that'll be 1 of the x-intercepts, and then find where 2x to the 1/3 minus 5 equals 0. So set that equal to 0. Add 5 divided by 2, so you get 5 halves equals x to the 1/3. And let's see, you remember what to do here. That's right, you're going to cube it. Raise both sides to the 3rd power. And get 2.5 to the 3rd power. And then you'll be good. That'll be some weird, let's use a calculator for this. 15.625 you want to be exact. Again, we raise both sides to the 3rd power. I have x 15.625. And so your other intercept will be at 15.625, comma 0. All right, so that's just the x-intercepts. Fun's just starting, so let's find the y-intercept. For that, we just find the function, find f of 0, find when x, find the value of the function when x is 0. That's simple. You just plug in zeros, it'll be 0, 0, 2 times 0 minus 0. And sure, it's already right here. So I don't even know why I did this again. Doesn't hurt. Okay, so we got those. All right, now let's do the calculus. Let's find the first derivative. Yeah. F prime of x. Power rule, 5/3 times 2, so 10/3 x. The 5/3 minus 1 power will leave me x to the 2/3 power. 4/3 minus times 5, so 20/3 minus 20/3 x to the 1/3 power. Okay, and then find some critical values. Let's identify possible critical values. Sometimes I call them critical points. I don't think it's really a big deal with the terminology, critical values. So find where the derivative is equal to 0 or undefined. So it's fine where it's equal to 0. So we set this equal to 0. And let me just go over here. So we get 0 equal to this whole thing. Let me save some work. So 0 equal to this. So let's factor some stuff out. Let's factor out well, we don't have to factor anything out. It'll just be 0. What am I thinking? Because it's just 0 times anything to any power 0, 0. And then that'll be, and you could factor out, I guess, the x to the 1/3. Let me actually do that. But you'll still get 0. It's just to show it more clearly. So x to the 1/3 times 10/3 x to the 1/3 minus 20/3. So you're going to have one of the critical values be when x is 0. And the other one, if you can find a 0 here. So let's see, let's hopefully the numbers work out nicely. So we're going to set 0 equal to this thing in here. So 10/3 x to the 1/3 minus 20/3. So adding 20/3 each side, we get 20/3 equals 10/3 x to the 1/3. So you can basically get rid of these 3's and multiply those will go away. It's 20 equals 10 divided by 2 or divided by 10. So you get 20 over 10 or 2 equals x to the 1/3. And again, we just cube both sides to get x. And what do you know? Get our next critical value. Let's actually put it up here. X, remember, this is just 2. 2 to the third, it'll just be 8. So our other critical value would be x equals 8. All right, cool. Works out a nice whole number. Now let's find the second derivative at double prime of x. We'll take the derivative of this guy. So 2/3 times 20/3. So 20/9 x to the negative 1/3. One-third times 20, so minus 20 over 9. Wait a minute. Yeah, minus 20 over 9. 9x to the negative 2/3. And then we find where the possible inflection points are. So we want to find possible inflection points. For that, we want to set the second derivative equal to 0 or find where it's undefined. Find where it's undefined. It's funny. I don't know why this pencil's acting really weird. Or whatever. All right, make this equal to 0. Now let's make this as a let's make these powers and let's put them in positive powers so you can see that they're in denominators, that they are in the denominator. So we're going to have 20 over 9 times x to the 1/3 minus 20 over 9 times x to the 2, or yeah, times x to the 2/3 in the denominator. And so then we can find where the second derivative is 0 or undefined if we can make these both equal. And also if we let's find where it's undefined first. It's gonna be undefined when x equals 0. Divided by 0, ruin everything. Undefined for x equals 0. And let's find where this is equal to 0. So f double prime of x equals 0. So let's do some fancy math here. So what can we do here? Let's make these both over x. No, let's make these both over 9x to the 2/3. So we're going to multiply this by x to the 1/3. So we're going to have 0 equals 20 x to the 1/3 over 9x to the 2/3. Because again, we're multiplying this by x to the 1/3 or x to the 1/3 times x to the 1/3. Let me just write it out. Let me highlight it so you can see what I'm doing. X to the 1/3 times x to the 1/3, just to save some work, because then we'll get the same denominator. Then minus 20. This is all over 9x to the 2/3. Then we just solve the top for the 0. So make 0 equal to 20x to the 1/3 minus 20. Factor out the 20, and then you'll get 20 times x to the 1/3 minus 1. And now it'll just be when x equals 1. Because 1 to the 1/3 is 1, so x equals 1. All right, so look at that. That looks very satisfying when you do all those calculations and everything is working out. So we got values you want to test at. We want to see what's going on around 1, 0, 8, 0. Again, we already got that. Really those 4 numbers, or those 3, because 0 repeats. So that's where we're going to break up our intervals. So let's set up a table. I like to use the horizontal table where the top row is my interval, followed by let me test the value. And f prime of x, and f double prime of x. And then let's actually do f of x too. Add that, and then we'll do the graph of f of x. The picture. So intervals. So we're going to break them up at 0, 1, and 8. So we're going to go from -infinity to 0. And then what we're going to do here to make this a little easier to see how the what's going on at these critical values, we're going to leave a column for just x equals 0. Oh, nice. And then we're going to go from 0 to 1. Then we're going to also leave a column for x equals 1. So we can see what's going on there. Then we go from 1 to 8. That's not an 8. That's an infinity. That's an 8. And then we're going to leave a column for x equals 8. And then we go from 8 to infinity. And this super cool table, you're going to see the whole thing all together. One user friendly matrix sort of thing. All right. So let's pick x values in these intervals. So let's pick x equals -1. Here, of course, we'll have x equals 0. That'd be that same number. Let's pick 0, halfway between 0 and 1, so 1/2. This will be x equals 1. Here we'll pick x equals 2, x equals 8, of course, and let's pick x equals 10. Remember, pick any x values in those intervals. Pick ones that are going to make your math lives easier, of course. Doesn't have to be those ones, though. And let's now calculate what the value of the derivative is for these x values, what the values of the second derivatives are, and what the values of the functions are, if it makes sense when we get there. Let me rewrite that. So let me do the first one. I'll show you the first one step by step. So we want to find f prime of -1. So f prime of -1. So we're going to plug -1 into the derivative equation, which is over here. And you want to see what's going on at what's the value there. So f prime of -1, you'll get -1 to the 2/3 times 10/3. And these will be a little tedious. So you can see it all in the calculator. So and you're going to get about 10. You're going to get exactly around 10. I broke the problem up. You get about 3.33 minus and negative is like 6.7, so about 10. Whoops. And again, what we really care about is the sign. So this is positive, so positive. You can do the calculation if it's not too tedious, but we care about the sign mainly. So I'm gonna time travel. So go ahead and calculate those derivative values, and then come back and check in just a second. Right, so then what we get are these values approximately. So we get a positive, a negative, and a positive number, those. Now again, don't stress out too much about them being exact. We really just care about the sign. And just be careful that you don't, make a little careless error. But use your calculator if if you're confident in your work, and usually pick numbers that are easy to work with. Like I probably could have picked like different numbers. It probably would have been easier to pick like -10 or -1,000 and 1,000, but in either case you should get these values. Now let's find the second derivative at those values as well. And I'm going to time travel again, so go ahead and calculate those, and then you can check in just a second. So pause the video right now if you want to practice this. All right, so then for your second derivative values, you should get a negative and a negative number, and a positive and positive number for those. And then let's look at what's going on with the actual function. So let's draw a sketch, or let's draw what the graph is doing here. So the first derivative is positive, and the second derivative is negative. So if the first derivative is positive, the graph is going up, but it's concave down. It's the second derivative. Here, this first derivative is negative, so it's going down. And the second derivative is still negative, so it's concave down still. First derivative is negative, the graph is decreasing, it's going downward. Here, the second derivative is positive, so the graph is concave up. And the first derivative here is positive, so the graph is increasing, going up. And the second derivative is also positive, so it's concave up as well. All right, so now let's see. Since there's no undefined values in the domain, there's not going to be any vertical asymptotes. So here, let's see what we got going on with the graph. It's increasing to the left of this x value and decreasing to the right. So then this is going to be a local max, because it's going upwards and downwards. Now here, at 1, we're decreasing to the left and we're decreasing to the right. So it's still going downward. So it's neither local max or local min, because it's not going up and down or down and up. But we look at the inflection, or we look at the concavity. The concavity changes from downward and concave down to concave up. So this is going to be an inflection point. Inflection point. All right, cool. The change from concave down to concave up. The concavity changes here. Over here, the concavity doesn't change. It's concave down on both sides. And over here, the concavity doesn't change anymore. But here, the graph goes from decreasing to increasing. So from down to up. So we have a local minimum here. Local min. And so then it's going to be worth our while to find what the values are. So when x is 0, we find f of 0. So we just plug 0 into here. And they're going to have 0. So f of 0 is 0. So local max, f of 0 is 0. So local max will be at 0, 0. Nice. Inflection point. Let's find what f of 1 is. Plug 1 into the function. We'll essentially get 2 minus 3, or 2 minus 5, should be negative 3. So we have an inflection point at 1 and negative 3. And the local minimum, plug in 8 into the function. Plug 8 into here, we'll do some fancy algebra. And then we're going to get that it's going to be negative 16. Parentheses around here. So local min at 8 and negative 16. Whoa. Now let's go. Let's just go ahead and do the fun part. Let's draw a sketch of this. Monthly grid paper, graph paper. And let's put it all together. See all of our hard work pay off. Okay, so let me draw my graph. Best as I can. We'll make it fit. Right. I really like graphing actually. Call me a nerd, but something strangely satisfying. Right, there we go, X, Y axes. If we zoom out, maybe that'll be easier to see it. Okay, now camera. Okay, so we have a local max at 0, 0. Let's just put a point here, 0, 0. Local max. Inflection point of 1, negative 3. Inflection points. And local min at 8, negative 16. Okay, that's going to be way out there. So 1, 2, 3, 4, 5, 6, 7, 8. So local min. 0, 0. 1, negative 3, and going down here at 8, negative 16. And so what the graph is doing, see, it's increasing on the left. And this is a local max. So I can do this. Concave down. So it's going to be doing something like this. You want to now again the other values on the graph. This is just a sketch. So we're doing something like this on the left. Okay. And then what it does is that it switches from concave down to concave up here. And it does this whole thing, goes like that. Bang, it starts increasing. And we have we have our other x-intercept at 15.625. So if that fits 1, 2, 3. It does fit. 15.6250. Just barely. Let me write it more clearly. So maybe this bothers me. 15.625 comma 0. And let's see if I can make this go right through that. There we go. This is a sketch. That's the general idea. See, concave up, concave down, switches concavity here. And there we go. There's your function. That helps. Hope that